Okay, so we're going to have a look at a basic introduction to wireless systems with a typical focus on IEEE 802.11b, G, and N. At the end of it, we'll do a little bit of an introduction to some practical things around configuring a Cisco Aironet. Okay, so this is the challenge that we have. Much of the infrastructure we've actually created is around wired devices. So what we need to move to is really towards wireless devices. But there are many issues that we have, especially to do with security, authentication, bandwidth. Our wireless systems often have limited support for things like quality of service, for real-time traffic. They can have a limited support bandwidth as opposed to wired networks, and also they're not quite as scalable as the infrastructure we see with wired devices. Along with this, they can be open to denial of service interference, and also there is a very crowded spectrum that we have where everyone's sharing the same media. And what we have is that at the core of the network, we typically move into the core and we increase the speed. So the core of a network might be running at 10 gigabits per second, and then we move out to 1 gigabit and then out further. So the range of the network that we have increases ever more, and that we get more and more devices connecting into our systems. So access points can connect at the periphery of the network, but increasingly they will actually connect right into the core of the network. So the different types of LANs that we have, wireless LANs that we have, is obviously the traditional mobile technology. So that's with the GSM network, which was our traditional phone network, and now onto 3G, 4G, and even 5G. We have wireless networks that, as we'll find out, is 2.4 gigahertz typically, and it's IEEE 802.11. Bluetooth is fairly common for creating local connections with devices, especially in pairing devices such as a phone to a speaker and a phone to a microphone and so on. Then we also get infrared and optics. And we may see ultra-wideband systems which will give a high throughput of data within small areas. And along with that, we also get a technology called WiMAX that will allow us to be able to interconnect what is known as the last mile. So here is a number of technologies. We have our cellular technologies. We have our fixed WAN technologies. Then we have our wireless LANs and our wireless personal area networks, or PANs. So up here we've moved from 2G through 3G up to 4G. The rates are still fairly limited that we get, but it gives us fairly good coverage and good connectivity, and especially useful when our wireless LANs won't connect. In between here we have WiMAX, which gives us excellent range. So the range goes up here. So it doesn't give us as good range as we would with 4G, but 802.16 or WiMAX gives us coverage over a large area, a large physical area, typically measured by tens of miles. Then for a more local area wireless network, we have our Wi-Fi, our 802.11 standard here. Typically 100 meters or so is a good scope for our connections. And then at the bottom we get an excellent coverage from Zigbee up through Bluetooth and then onto ultra-wideband. So ultra-wideband can take us up to and over 1 gigabits per second. As you can see here, typically what happens is that the wider the range of the technology, that's the more the radio waves spread, then the lower the data rate that we can actually transmit. Okay, so when you think about it, we have really something like this. We might use piconets. These are personal nets to create wireless networks. That's with our Bluetooth. We can then bind this with a wireless LAN to provide some sort of backbone that would allow us to be able to move around a geographical area. And then our cellular type technology, our mobile phone type network, 3G, 4G, can provide the backbone. So with this, we can move through the different regions, still stay connected, and we can move back in. So the back end here is providing us with the always-on type technology, but it's probably lower bandwidth. As we move in, then we get higher bandwidth. So what we often have with our wireless networks is that we have cellular type infrastructure. So inside each cell, we have connectivity with our base station, and we connect to the base station, which has the strongest signal. And this allows us to move through the cells, and as long as they overlap, then it's possible for us to always keep connectivity. But within inside this, our wireless networks, we can have a smaller networks within inside the large area. And if we go down to a smaller area, again, we can have smaller piconets within inside our personal networks within inside each of the wireless area networks. Okay, so this is the metropolitan area networks. This allows us to move through cities and so on. The WANs provide us with the local networks, and then the personal wireless area network allows us to create very small regions of connectivity. Okay, so let's look at some of the basic fundamentals with Wi-Fi. What we have with a radio wave is that we have an E field, or the electric field, and then we have the H field, or the magnetic field. And these provide us with our propagation. So the E field moves at right angles to the magnetic field, and then we have a direction of propagation. So this is known as the right-hand rule. We have electric fields, electric field, magnetic, a magnetic field, and then the direction goes perpendicular to both of those fields. And the basics of this is that the velocity, or c, if it's the speed of light, the velocity is equal to f lambda, where lambda is the length of the wave, f is the frequency in hertz, and v is the speed in meters per second. If we're dealing with light, then we define light as c, or 300 million meters per second. Okay, so if we want to calculate lambda, we just take this formula, and if it's traveling through space, free space, then it becomes c over f is our lambda. And that provides us with the physical length. If we were to measure the length as it appears in our wave, then that would give us our physical length of the actual wave, and that's known as lambda. And inside our electromagnetic spectrum, that we have different bands, different types of waves that we see, and all electromagnetic waves. As we go up, we increase frequency and we reduce the wavelength. Okay, so the wavelength here is large, might be measured in miles, and down here is extremely small. Frequency is also extremely large here, and is small then. So as we go through, then we go through radio waves, AM, up through FM. FM is about 8 to 8 megahertz, right through analog TV up to about 200 megahertz. GPS runs about 1 gig, and then we move into the microwave region. So with microwave region, our waves are typically a few centimeters long, okay, or it could be millimeters. So we go from centimeters down to millimeters then. Okay, so that's centimeters, and then we're down to millimeters. So around here, we're looking at about 5 gigahertz or so. And then we move into infrared. The frequencies become very large. Very difficult for us to define these as values. So we typically refer to waves in this region in terms of their wavelength, where in this region we typically talk about their frequency. Okay, so we would hardly ever say that a radio wave has a certain wavelength. We would typically say a radio wave has something like 535 kilohertz, and not the wavelength, because the wavelength can be over, as you can see here, the wavelength is the wavelength is very large. That's 1,000 meters for this type of wave here. Okay, so up into the infrared, then we have a very small spectrum of light in there, infrared through ultraviolet, up into X-rays and then gamma rays. An approximation we can use is that roughly the bandwidth that we can transmit is about 1/10 of the carrier frequency. So as we go through the spectrum, we have increasing amounts of information that we can actually send. Obviously it becomes very difficult when we go into this region, and we might use light pulses. But in this region here, the higher the radio wave, the higher the amount of data that we can actually transmit inside that carrier wave. So for AM, we're only looking at about 170 kilohertz, and we go up to microwave, we can go up to about 240 megabits per second. And this is the spectrum here. Roughly, this is the amount of power that we would see if we looked at our spectrum. TV is a very strong signal, so is a cellular. GPS doesn't lose so much, and so on. But ultra wideband actually doesn't actually have a frequency. It tries to spread itself across the whole of the band and then go below the noise floor. So this allows ultra wideband not to affect any other communication mechanism that we might use. In terms of the RF bands, we go from low frequency right up to microwaves. So here we have low frequencies and extremely long wavelengths, up to here where we have high frequencies and fairly short wavelengths. To give you some idea, an antenna is about half a wavelength. The wavelength here is about 5 centimeters or so. So our antennas are typically measured in a few centimeters. Where up here they can be measured in many hundreds of meters. The waves here propagate very well over large distances. So long wave radio can actually bend itself around an object, and you typically find very long propagation lengths. When we go up to TV signals typically need a line of sight. If there's a hill in between, then the wave can't really bend over it. So we typically need a line of sight connection for that. And then when we get to microwave, we don't want any obstacles really in the way for that. Okay, so let's look at a few issues in terms of wireless networks. So we have the problem of multipath. So multipath, as we'll see, is where we get signals racing each other and can actually cancel each other out. We get radio waves that can actually collide with each other for the same frequency, they can collide and cause distortion. We can have an out of range threshold, so it's possible for two computers on a wireless devices on a network that can't see each other because they're at the outer edges of the network. And also other equipment such as fluorescent lights and microwave ovens can actually affect the wireless network. Okay, so absorption and reflection is one problem. So it's good sometimes because we can bounce our signals off metal objects. But in other cases it can cause multipath. Along with this, if it's a non-conductor, the wave will not reflect off it, but it will go through it, but then it will be absorbed. So things like concrete absorb radio waves extremely well. And we also get fading of the signal. The signal will eventually degrade as it propagates. Okay, there's an inverse square law there, but the power will generally fade the further we are away from a wave because it's spreading out. So the multipath is that we could have a transmitter here, and we can have a path here. There's another one here, and then another one can be in another place, and we can even get a direct line of sight. If we're very lucky, when all the waves get there, they'll all reinforce themselves back. But if we're very unlucky, then two out of frequency phases can actually come back together and produce a null spot. So we actually see this when we map our radio space. We'll actually see that there are small spaces where there's a null, and this is to do with the radio waves coming together and cancelling each other out. Often it's quite easy. We just need to move a few centimetres away from it and we're actually okay again. Or we move the antennae a little bit and that can overcome the problem. Okay, so the two main technologies that we have with inside the sending of data over a wireless network is time division multiplexing. So with time division multiplexing, what we have is a time slot at which we transmit. So this chap here has the first time slot, and then he's sending to him. So he will look in that time slot. This chap here is transmitting a second time slot, and then that will be read by that one. So this is known as time division multiplexing, or TDM, and it's used in GSM, 3G, and also with inside the network switching. The other method that we have is we have frequency division multiplexing. So with this we use different frequency bands to be able to transmit our signals, and then the receiver tunes into the frequency that we're actually transmitting on. So this allows us to be able to transmit several channels at the same time. Okay, so for frequency division, what we do is we split the available bandwidth into a number of bands, and then we actually can connect into the different bands. So a typical number of bands with standard Wi-Fi is about 14. So there are 14 different frequency bands that we can connect into, and as we migrate through the network we can hop between different bands. It also allows the different bands not to interfere with another band. So for our phone network, we've went from 1G to 2G, getting a bit better there. Then 3G gave us several megabits, and now we can get tens of megabits per second through 4G, and we now have our always-on connectivity. So often with our mobile phone network, what we have is that we connect to base stations, as we migrate through the network, we connect to the strongest base station, and that will give us connectivity between the different cells that we have here. And often what we have is that we make a connection into the GSM network, which takes us back into the telephone network or out onto the internet. So our switching systems are actually moving between our old telephone system and then also into our internet technologies. So if we look at it, how many different frequencies, so if we had a number of frequencies, let's call them different colours, how many different colours do we need to make sure there are no overlapping cells with the same colour? Well, the answer to this is 3. So we can see in this case, if we had a patchwork quilt with 3 different colours, we can colour them all in and never have 2 colours overlapping each other. And this is the way that Wi-Fi networks typically work. What we don't want is that one to overlap with one, because the signals will interfere with each other and reduce the throughput. So in this case, we can have 3 different frequencies, and we move through the frequencies as we go through the system. Okay, so in this case, the device is connecting to 3, and then as we move there, we can move into 2, and so on. The other method that is used it's often used inside wireless networks, is frequency hopping or spread spectrum technology. With spread spectrum, what we do is that we have a certain starting frequency, and then we move the frequency back and forward in a certain way. And as long as the transmitter and the receiver can actually follow the signal, then it's actually received correctly. So this stops us from getting jammed on certain frequencies, and we can transmit several channels at the same time on the same frequency. Okay, so it avoids us from getting jammed on a certain channel. We can also avoid any noise that's there. So because we're moving back and forward, we can avoid any bits of the spectrum which are quite noisy. And also it's used in military type situations where we can actually move. As long as the transmitter and the receiver know how to move, then our enemy shouldn't know how we're actually spreading our spectrum, spreading our signal across the spectrum. Okay, so this is the setup of a normal 802.11b type setup. We have these small channels that we set up, and there are non-overlapping channels. 1, 7 and 13 are non-overlapping. The other ones will overlap in some sort of way. So the channels 1, 2, 3 and 4 will overlap, 7, 8, 9 will overlap, and so on. Okay, so now let's look at IEEE 802.11 networks. So 11A defines 5 gigahertz and gives us 54 megabits per second. It's used for fairly good coverage, and we get smaller antennae because it's 5 gigahertz. B transmits at 2.4, and most of the other frequencies are at 2.4 gigahertz. And most of the Wi-Fi that we connect to is 2.4 or 5 gigahertz. So with G, we increase the speed up to 54 megabits per second. And now with 11N, we can go up to 540 megabits per second using a technology called the MIMO, which is multiple in, multiple out, where we can have a range of antennae and we can actually take different paths and create different channels. So we actually use the reflections that we saw earlier to our advantage. Okay, so 11B, in Europe we have about 13 channels for 11B. So those are numbered 1 up to 13. Okay, 1, 8, and 13 are typical channels that we might use. And then we go for different data rates. So the further we get away, the lower the data rate actually becomes, and we'll use a different type of technology for these. Okay, so for a wider range, for a small range, for a small range, we can have high throughput, and then for our larger ones, we reduce the throughput. So a wireless network which has a wide range, the outer node will generally bring the whole node down because the other nodes have to run at those speeds. Uses spectrum and a number of modulation techniques to be able to achieve the different rates. So the main things that we have to set is our authentication algorithm. And the authentication algorithm will actually define how we authenticate ourselves onto the network, such as a username and password. The channel that we're going to use, a fragmentation threshold. So it's the problem with wireless networks is they're based on Ethernet, and Ethernet produces very large data frames, 1500 bytes or so. So sometimes it's better to chop these into little fragments and then send them one at a time. You often use much more of use the bandwidth more efficiently if you actually do that. So the fragmentation threshold will allow us to split into smaller fragments and then rebuild them at the other end. And then we have the network type, which is either an infrastructure network or a basic ad hoc network. We'll look at later. Okay, so there's two other things, preamble setting. So in Ethernet and wireless networks, we get a whole lot of ones and zeros as a preamble to say that the device is going to transmit. We can keep this to a minimum if we want by creating a short preamble, and that's for faster communications. And then there is a thing called the hidden node problem, and that's for ready to send and clear to send. So an access point will send the device will send ready to send, and then the access point sends a clear to send to say that it's ready to send. If the devices are separate from each other, they might not actually see the signals going back and forward. So this is where we get the hidden node problem. Okay, so we've gone into more detail in other units on this, but let's actually take a quick look at a sample device. So in this case we have a Cisco Aironet, fairly standard device, fairly robust devices. They have a metal casing and we have our antennas there for that. Typically running at 2.4, or we can get 5 gigahertz from there. It then connects into a switch and then into the core of the network. So it's a layer 2 device, but it can also operate at layer 3 through what's called the BVI port. So the BVI port is the way that we connect into the device to be able to configure it and set it up. So this is the virtual port, and it's assigned an IP address. We can also set up our radio port, which is layer 2, and we have our Ethernet adapter there. Okay, so the BVI is the virtual interface that we have. So for the radio interface, we set things like the channel, the data rate, and the maximum number of nodes that could connect on our radio network. And for our Ethernet, we can set up things that will define the speed of the network. Okay, so let's have a look at a quick configuration here. Okay, in this case we're setting up BVI1 with a certain IP address, and then we're doing a no shutdown on FA0. No need to set an IP address for the Ethernet port, and then we are setting the speed of that, and then we're doing a no shutdown on the radio port. So let's go ahead and have a quick try at the hide this. Okay, so we have a web page that's set up that we can use from there, and we'll just get started. So it's like any Cisco device. We'll just enable. If you actually want to see what the challenge is in this case, then you should be able to get some details from here, and any of the settings of the device from here. So the first thing that we'll do is we'll do show version. Show version will give us some idea as to the setup that we have for our Cisco device. We can see it's this model here. There's the processor, this is what it's got, and we can actually look at some of the details around the serial numbers. And then we can do a show running config, and that will show us what our settings are for our device. Okay, so we can see there is a .11 radio interface. Okay, so we can just go ahead and configure it. Host name as Anko, and we should get a correct symbol there. So we can then go into interface. You can try the tab BBI1 and IP address 202.13.112.3.255.255.255.128. Okay, so that should go there, and we can set up the description of the interface to give it a name. That's it. Okay, so you should find the running config should be changed to actually see what the listing actually is. Okay, so that's a basic introduction to our Cisco Aironet, and hopefully we'll be doing some practical things in the lab related to this. Okay, so that's been a very brief introduction to wireless networks, and we'll build on this to look at some other things.